Your first flight into space on STS-49 was also the first flight of the Space Shuttle Endeavour. Can you describe the purpose of that flight?
I sure can, Stefan. First, thanks for having me on this program. It's really a great pleasure to join you. But we had several objectives on this flight. One was the first flight of Endeavour, so it was a shakedown cruise, if you will, for a brand new space shuttle to make sure all the systems worked. And fortunately, Endeavour performed almost flawlessly. The couple minor things we had to deal with were things that we got done before the main part of the mission and then at the end of the mission, and didn't interfere at all with the mission objectives. The big advertised purpose of the flight was to, and the main thrust was to go up into low Earth orbit, take a rocket engine with us in the cargo bay, and rendezvous with a telecommunications satellite called Intelsat 6 that was supposed to be put in a geosynchronous orbit, but because of a malfunction, was stuck in a low Earth orbit of 250 miles, which meant it couldn't do its mission from there because it needed to be up high enough to be stationary over the Atlantic Ocean to relay television and radio signals between the US and Europe. And so we carried up a spare rocket motor. The challenge was to attach the motor to the satellite. And the satellite had not been designed to ever be touched by human beings. It was launched on an unmanned rocket. And so it didn't have any of the normal features that you would put on a satellite that you intended to go and grab with the shuttle manipulator arm. And so we had to come up with, the engineers had to come up with a solution for that. We had another experiment on the flight that was called ASEM, ASEM, which stood for Assembly of Space Station by EVA Methods. And at the time, in 1992, and actually back in 1990, when they started to plan this flight, there was still a debate on the best way to build the truss on the International Space Station when it was eventually to be built. And this was, of course, at least 8 years before its first launch. One concept was to build the truss on the ground in segments and launch it fully assembled. This meant it would have to be pretty heavy, though, because it had to withstand launch loads, potential abort modes, which would mean re-entry and landing loads as well. And so it was going to be bulky and heavy, and that would imply that you might have to fly extra assembly flights to get it up on orbit. The alternative consideration was to take up very lightweight elements. I like to refer to them as Tinker Toy-like, and in the cargo bay, and have astronauts go outside and assemble them on spacewalks and build the truss in orbit, just using essentially sticks and balls that they could connect them together with. The advantage of that would be very lightweight, simple, less expensive to design and build. Disadvantage would be the amount of time to assemble it on orbit. And in that regard, we weren't quite sure what the difficulty, the factor would be for assembling. So on this particular flight, STS-49, all 4 of our EVA astronauts trained to build a small portion of a truss and then take it apart and understand the time factors and difficulties associated with that. We had another little experiment on board that turned out to be significant. That was a software package designed by Rick Heeb, one of our crewmates. And it was a package designed to improve the efficiency of rendezvous, or coming up close to a satellite or a space station. And by efficiency, I mean to use less fuel, because fuel is a precious resource in space. You only have what you take up there with you. It turned out to be a significant part of the mission because we learned early on that that software worked very well. And we ended up actually using it on our 3rd rendezvous. We had only scheduled 1. And so the efficiency and use of fuel became very important on the mission. And Rick's software really helped save the day. And I think the last objective that was an important one, again, looking forward to the International Space Station time period, had to do with we were understanding then that to assemble the space station on orbit was going to take multiple spacewalks. And we hadn't really done that to date in the space shuttle program. And spacewalks can be very tiring on the astronauts that go outside. And if you're limited in time for how long you can be on an orbit, and you had to do maybe 3 or 4 spacewalks for assembly mission, you didn't want the same 2 people doing them over and over again, because you had to give them a day of rest off typically in between spacewalks, because it is strenuous. So for the first time in the program, we scheduled to have 3 spacewalks scheduled, 1 to rescue the satellite and put the motor on it, and then 2 spacewalks to practice the assembly and disassembly of the truss. And we trained 4 people to be able to go outside and carried enough equipment to support 4 spacewalks. So the right size spacesuits, et cetera, for them to go outside. And typically you'd only carry 2 spacesuits and only 2 people would be qualified. So the objective was to do 3 spacewalks and alternate spacewalking crews, just as we thought we would do when it came time to assemble the space station. So those were the major portions of the mission that we trained for.
The retrieval of Intelsat 6 was rehearsed many times on the ground, but things didn't go as planned. What about the training was not the same as the real-world mission?
Well, I think the training was exceptional. There was, and this was all in hindsight when we looked back at why did we have the problems we had, which I'll first describe. And it really had to do more with the tools that we had available for us to train on, and specifically for Pierre, who was the man at the end of the shuttle arm trying to do the capture. So I mentioned earlier that it was this satellite was never meant to be visited and recaptured by humans or a space shuttle. And so the engineers had to come up with a design that would allow us to do that. And of course, you can't walk around in space, so you can't just go up there and grab the satellite, even no matter what you invent, and walk it over and set it on top of the rocket motor we had carried up. You had to put a device on it that would allow us to use the shuttle robotic arm to grab that device and position the satellite on top of the rocket motor. So the plan was for one of the astronauts, Pierre Thuot, would carry up with us this long bar, metal bar, that had some sophisticated mechanisms inside it that had claws, essentially, that would grab onto a ring on the bottom of the satellite, known as the thrust ring. And the satellite was spinning, by the way, so just to add to the level of difficulty, Pierre would be right up underneath the spinning satellite. He was on the bar. He controlled the bar by holding a steering wheel type device. And his objective was, and at the end of the bar was a pin that the shuttle robotic arm could grab onto. So the idea was attach the bar to the spinning satellite, stop it from spinning, and then let go, and then let the Bruce, who was operating the arm, grab the pin, and then we could move the satellite where we wanted to. So Pierre is holding onto the bar by holding onto the steering wheel, and he has to come up underneath the spinning satellite and push the bar up against the claws on the bar, up against the ring, and then fire the mechanism. It was automatically fired, but he could do it manually too. That would grab the ring. And then he would use the steering wheel to stop the spinning. And then the idea was he would let go. Well, he had to physically push the bar up against the spinning satellite. And even though the satellite weighed, thousands of pounds, and Pierre wasn't pushing that hard against it, because of the zero gravity condition we're in, weightless condition we're in, as he's pushing the bar against the satellite's naturally going to move ever so slightly away. And it's difficult to maintain that steady push because there's not a lot of feel that you have inside the space, one. And two, it was necessary to keep the bar close to that spinning ring because the tolerances on the claws were pretty tight. So if it wasn't pressed up against the ring exactly, the claws would close, but they wouldn't necessarily successfully grab the ring. So that's what happened when we got on orbit. Pierre did everything he had done in training, which had worked 100% of the time in training, and the claws would not grab the satellite. So we did some problem solving. We said, there's a possibility on orbit that was the problem, which led to us sending 3 people outside eventually, 2 to hold the satellite still while Pierre was able to push the bar up against it. But so you go back, what was wrong with the training? Nothing with the training, but it turns out that the simulator that Pierre used that was very well built. It was exactly the same moments of inertia and weight and structure and it spun that it simulated the satellite quite well. But to simulate weightlessness, that whole structure had to sit on an air-bearing floor. Now, if you've ever played air hockey, you know what an air-bearing floor is. It's got a bunch of holes in the bottom of the floor to blow air up in it to try to reduce the friction and air hockey on the puck that you're hitting around to make it move around the table. And in this case, to reduce the friction on this simulated satellite that Pierre is pushing against, because it has to stand on something on the ground in one gravity. Well, they thought they had got that good enough, and it's impossible to be perfect. But it turned out there was enough friction that satellite on the air-bearing floor between the satellite simulator and the air-bearing floor, that every time Pierre practiced it on the ground and he pushed the bar up against it, the satellite didn't move away, the simulator didn't move away, and the claws worked. But in space, where you had absolutely zero friction, that wasn't the case. So, the lesson learned there is you have to do a little more specific analysis on the sensitivity of the force you're putting on an object that's in space, that's weightless, and how it will react. And then make sure that your simulation of that on the ground is as close as you possibly could get to that. And if the tolerances are really tight, then you need to take that into consideration as well when you design your mechanism. I think there was one other issue, and that was Pierre noticed, and he commented on it after the first spacewalk. On the ground, the bar is quite heavy, and Pierre was in his spacesuit. He was actually being supported by a crane device because his spacesuit was heavy. So again, they were trying to do everything as realistically as possible. The bar was also being supported by a bit of a crane, and so to make it feel weightless in his hand. But you couldn't feel the moments of inertia as well as you could when you're in a weightless environment. He even had one in the swimming pool that he could work with, but there he had the viscosity of the water, made the bar feel different than it did in space. And so he commented on that as well. And that was a lesson learned on things you got to consider when you're handling a large piece of metal, as he was doing in space, and the difference the feel is going to be there as opposed to on the ground, where you can't handle the large bar without some support mechanism, or if you're going to handle it underwater, you have to deal with the additional friction in the water that will make it feel different than when you're outside.
Well, thank you, General Chilton, for answering these questions about the STS-49 mission.